So here we're still working on derivatives and specifically our understanding and our interpretation of derivatives. And we're going to consider just a slightly more complicated problem here. The problem is, again, our Six Flags problem from a previous lesson. So we have two functions here, and the way we're going to make it more complicated this time is we're going to use both functions at the same time. And we're still focusing in on primarily how our quantity is changing. Okay, so take a second, make sure you read this whole thing. Remember, we have E and L are standing for people entering and leaving the park, particularly the rate at which they enter and leave. That word rate is important. And then we are given this function h, which is E minus L. So really the question is going to be, what does h represent? So it looks like I need both E and L here. So what I've done is I typed them both into my calculator in my functions menu, my y equals. And I've done this here because we're going to use them again for my second question. So as always, when we're working with a calculator, I suggest you follow along with me on your calculator and make sure you can get it to spit out the same number. And we just want to do h of 17. That works. You had this on your summer homework, and you know how to do this. H of 17 equals E of 17 minus L of 17, based on what's given to me. So that means we're plugging 17 into both. And I'm going to do that using the grapher. So my second calc value button, and I'm going to type in 17. And your calculator is going to think a bit maybe, and you might get this error. It's going to say invalid. That's okay. The reason it's saying invalid is if you go to your window, you're probably on negative 10 to 10. So we just plugged in 17, which is outside of my xmin, xmax. So I can fix that. I can change that to 20 or something. It doesn't really matter. I just want to make sure 17 is included. And then it's going to have to think some more. And notice now my graph looks different because I changed the window. And once it's done thinking, you can do a second calc value and type in 17. And my calculator spits out a fraction here. That's fine. I'm just going to capture it. So it's my numerator over 41. And then I need L of 17. And notice I can tell that this is E because it shows up here. To get L, I just need to switch graphs. So I use the up or down arrow to do that. And notice now I'm on Y2. And Y2 is my numerator over 13. And because I need to do some interpretation, this word interpret, I'm going to want to make this just a number, right? So we're going to reduce that a little bit, simplify it. They kind of came out ugly, but that's okay. I'm just going to use my calculator to do that. So what I did is I typed in my value, and then I turned that fraction I got into a decimal. So I just typed in my two fractions, let my calculator do that math, and then I'll show you how to do that. So here's my result, and then I can hit math and then 2, and then it spits out that decimal for me. So my result is negative 380.281. And that's my h of 17. That's my answer. We still have to interpret that meaning. So that's why we annotated what these functions are, because that's going to help us figure out what our new function h is and what our answer means. And that's the most important work that we're doing. So our calculator just did all the work for us. We have to do the human work of explaining what we're talking about. Now, let's step back from this question. You may have some thoughts already about what this means. But if not, I'm going to draw an illustration for you. This type of problem is called a rate in, rate out problem. It's a very common AP calculus problem, and the reason it is so common is because it's a really great way of just testing your understanding of derivatives and rates of change, how quantities are changing in relation to each other. So imagine a bathtub, draw a bathtub. Mine is going to be simple because I'm not an artist and I'm using this computer screen. But we have a bathtub, it's going to be full of water, that's why it's blue. And imagine you're adding water to the bathtub. So that's water entering the bathtub. You can draw a little faucet on yours if you want. And then also imagine, at the same time, there's a hole in the bottom of the tub, and water is draining out. Okay, so that is a rate in, rate out type of problem. And it's exactly what it sounds, right? So if you're anything like me, you've had situations at home when you're taking a shower, right? And the drain's like kind of plugged in the shower, the tub starts to fill up with water a little bit as you're showering. That's a rate in, rate out type of problem. And what happens, right, is the water level starts to go up. And it starts to go up when the water is entering faster than leaving. So in is faster than out. And if we want it to go down, we want to take our shower in peace, we need the opposite, right? So that's the type of problem that we're considering. And really, it just means we just compare two derivatives is what we're doing. So in bigger than out would be an increasing water level, and then the opposite would be decreasing. Now, we're about to apply this now to our mathematical notation from our Six Flags problem. So we have the number of people in the park increasing would be when E of t is greater than L of t. And then decreasing would be the opposite. So now we know enough to figure out what our H means. So notice H is the difference between E and L. So H is in minus out. And we got a negative number. So that means our water level is the total number of people in the park, right? The number of people in the park here, that's my noun. And notice I had to think about what that was this time. It's not really told to us. Is decreasing, because we had a negative result, at a rate of 380 people per hour at t equals 17 hours. So that's my interpretation. So notice it's still the same interpretation that we're writing, just the work of finding that value is a little bit harder. So that is a rate in, rate out problem. We had to use two rates, E and L, to make a claim about a total number or a total rate of change. Now my next question asks, is the rate at which the number of people in the park is changing increasing or decreasing? And this is a hard question. So remember, our rate from our previous problem was h of t. So in this question, we want to know how h of t is changing. We need to consider then h prime of t, its derivative. And what is h prime of t? Well, h prime of t would be e prime of t minus L prime of t. It would be the derivatives of my original function. So this is hard. So we're looking at how the rate is changing, so we need the derivative of the rate. So if I need to consider that value, I already typed these in, so I can just use math 8 on my calculator. y1 minus y2 is rate in minus rate out. And it spits out, again, a negative number. So my response here would be the rate is decreasing at t equals 17 not because h of 17 is negative, but because h prime of 17. So that is challenging, and what is challenging about this is the precise language that we need to use. The rate at which the number of people in the park is changing, increasing, or decreasing. So it's asking us about h, that's the connection that we need to. The last thing I want to add is here's an example from Delta Math. So you're going to need this for your homework for this. And read the words here again. So we have water being pumped in the tank, just like my picture up here. Make sure you've read it. It says G is the amount removed, and Z is the rate water is added. So notice there's two different word choices there. They do not mean the same thing. So we need to read carefully so that we can think carefully here. If we want to find out whether the amount of water in the tank is increasing or decreasing, well, we need to consider rate in minus rate out. Okay? So rate in is easy. Rate in is z of t minus rate out is not g of t, right? G is the total. So if we want rate out, we want how much the total is changing. That would be g prime of t. So that's how we would set up this problem, and then we consider the sign of the result. So this is going to be challenging because we have to read the words carefully and connect them to the concepts that we're building.